Welcome. Today, we'll tackle the problem number 1694, reformat phone number. This is an interesting string manipulation problem that requires reformatting a phone number into a specific pattern. We'll explore different approaches to solve this step by step. Let's dive in. In this problem, we are tasked with reformatting a phone number to make it more readable. The phone number is given as a string that may contain digits, spaces, and dashes. Our goal is to transform this input into a standardized format by grouping the digits into blocks of size 3 or 2. First, we need to clean the input by removing all spaces and dashes. Then, we group the digits into blocks of size 3, starting from the left. If we reach a point where there are exactly 4 digits left, we split those into 2 blocks of size 2. Finally, we return the reformatted phone number as a string, with all the blocks joined by dashes. The input will always consist of digits along with optional spaces or dashes, and the output is expected to be a neatly formatted string. Let's look at an example to clarify. If the input is number equals January 23, 45.6, we first remove all non-digit characters, leaving us with the cleaned input 12345.6. Next, we group the digits into blocks of size 3. In this case, we can form 2 blocks, 123 and 456. Finally, we join these blocks with dashes, resulting in the output 123-456. This demonstrates how we process the input step by step to produce the desired format. Now consider a slightly more complex example with the input number equals 123.4-567. After cleaning the input, we get 1234567. We then start grouping the digits. The first block is 123, followed by a block of size 2, 45, and finally another block of size 2, 67. These blocks are then joined with dashes to give the output 123-45-67. This example highlights the rule about forming blocks of size 2 when there are no more full blocks of size 3 possible. In another example, where the input is number equals 123.4-5678, cleaning the input leaves us with 12345.678. Here, we start by grouping the digits into blocks of size 3, forming 123 and 456. However, we are left with exactly 4 digits, so we split them into 2 blocks of size 2, 78. Joining all the blocks with dashes results in the output 123-456-78. This demonstrates how to handle cases where the remaining digits after grouping consist of exactly 4 digits. The problem also comes with some constraints and edge cases to consider. The input string will always have a length between 2 and 100, and it will only consist of digits, spaces, and dashes. For edge cases, if the input has only 2 digits, the output will simply be those 2 digits without any dashes or spaces. If the input contains excessive spaces or dashes, such as 123, we still need to clean it properly and format the digits correctly. For longer inputs close to the maximum length of 100 characters, our solution should remain efficient and handle large blocks of digits seamlessly. This ensures that the grouping logic works correctly for all valid inputs. To solve the reformat phone number problem, the brute force approach offers a straightforward and intuitive method. First, we iterate through the input string to remove all non-digit characters, such as spaces and dashes, leaving us with only the numeric digits. Once we have this cleaned version of the input, we can group the digits based on the rules provided. If there are exactly 4 digits remaining, we split them into 2 groups of size 2. Otherwise, we continue grouping digits in blocks of 3 until fewer than 4 digits are left. The process involves appending these groups to our result as we go, and then joining them with dashes to form the final formatted string. This method is clear and systematic, making it a good starting point for implementing a solution. When analyzing the complexity of this brute force approach, we find it operates in linear time, or n, where n is the length of the input string. This is because we iterate through the string once to clean it and then again to format the digits. In terms of space, the approach also uses n, as we store the clean string in the formatted result. However, we can consider a more optimized approach to streamline this process. One key observation is that the brute force approach already processes the string efficiently in linear time, but we can simplify the logic by appending digits dynamically as we traverse the input, rather than manually splitting them into groups. By leveraging slicing techniques or modular arithmetic, we can make the implementation cleaner, especially when handling the edge case of 4 remaining digits. This optimized version combines cleaning and formatting into a single pass, potentially reducing the code complexity while maintaining the same overall efficiency. After comparing these methods, the brute force approach emerges as the chosen strategy for its balance of simplicity and effectiveness. It solves the problem in linear time, and its step-by-step logic is straightforward to implement and debug. While the alternative single-pass method is slightly more concise, it introduces additional complexity, particularly when dealing with edge cases like the last 4 digits. The brute force approach's clear structure ensures that the grouping rules are easy to follow, and any errors can be quickly identified and resolved. The trade-off here is between verbosity and maintainability, with the brute force approach leaning towards being more verbose but easier to work with. The aha moment in this problem is recognizing that the task boils down to iterating through the digits and handling one specific edge case. Once the input is cleaned, the grouping rules are deterministic, making the brute force approach a natural choice for this problem. Finally, this approach achieves an optimal balance between efficiency, simplicity, and ease of implementation. The time complexity remains O(n) as we perform a single iteration to clean and format the digits, and the space complexity is O(n) due to the storage of the formatted result. These metrics ensure that the solution is performant even for larger inputs. By focusing on the brute force method, we retain clarity and maintainability, making it easier to implement and debug while still meeting the problem's requirements. This combination of practicality and efficiency makes the chosen solution ideal for addressing the reformat phone number challenge. Here, we are tasked with reformatting a phone number string into a specific pattern. The input string may include digits, spaces, and dashes, but we need to produce an output with groups of digits separated by dashes. To do this, we follow a series of rules. First, we remove any non-digit characters, such as spaces and dashes, leaving only the numeric digits. Next, we group these digits into blocks of size 3. If, at the end, there are exactly 4 digits left, we split them into 2 groups of size 2. Finally, we join all the groups with dashes to form the formatted string. To start, the first step is to clean the input. This involves iterating through the string or using a filter operation to remove all non-digit characters. For example, if the input is 123 to 45678, the clean string becomes 123456778, which sets the stage for further processing. Once we have the clean string, the next step is to set up the variables needed for grouping the digits. We initialize an empty list called groups, which will store each group of digits as we process the input. Additionally, we define an index pointer, I, to track our position in the string. Next, we focus on processing groups of size 3. Using a while loop, we repeatedly extract 3 digits at a time from the clean string, as long as there are more than 4 digits remaining. With each iteration, we append the substring cleaned_string, I plus 3, to the groups list in increment I by 3 to move to the next block of digits. For instance, given the clean string 123456778, the first iteration extracts 123, adding it to the groups list. The second iteration extracts 456, resulting in groups equals 123, 456. This continues until fewer than 4 digits are left. After processing groups of size 3, we handle the remaining digits in the string. If there are exactly 4 digits left, we split them into 2 groups of size 2 to adhere to the formatting rules. If fewer than 4 digits are left, we simply append these as a single group to the groups list. For example, if the remaining digits are 78 foot, we add it as one group. If the remaining digits are 1234, we split them into 12 and 34. Once all the digits are grouped appropriately, we proceed to combine the groups into the final formatted string. This is done using the join method, where we concatenate the groups with dashes. For example, if the groups are 123, 456, 78, the final output becomes 123-456-78. This step ensures the output matches the desired format. There are a few key insights to consider when designing this algorithm. First, cleaning the input at the beginning simplifies the logic for grouping digits. By removing non-digit characters like spaces and dashes up front, we ensure the processing steps are straightforward and consistent. Second, the special handling of 4 remaining digits is crucial for meeting the formatting requirements. Without this rule, a string like 1234 might be incorrectly formatted as 123 to 4 instead of 12 to 34. Additionally, the use of efficient data structures plays an important role. By storing intermediate groups in a list, we can dynamically add new groups and easily concatenate them at the end. The clean string, stored as a simple string, allows for straightforward slicing and indexing operations during processing. Now, let's analyze the complexity of the algorithm. The time complexity is O(n), where n is the length of the input string. This includes the O(n) cost of cleaning the input, the O(n) cost of grouping the digits, and the O(n) cost of joining the groups into the final string. The space complexity is also O(n), as we store the clean string and the groups list, both of which scale with the size of the input. Additionally, we should account for edge cases to ensure the algorithm is robust. For an empty string, the output should also be empty. If the input contains no digits, such as, the output should still be empty. For very short strings, like 1 or 12, the algorithm should handle them correctly, outputting 1 or 12, respectively. Special care is required for strings with exactly 4 digits, which must be formatted as 2 groups of size 2, such as 12 to 34. Finally, the algorithm must ignore special characters like @ or n during processing. Let's walk through a concrete example to solidify our understanding. Suppose the input is 123 to 45 6789. First, we clean the input to remove non-digit characters, resulting in 1 2 3 4 5 6 7 8 9. Next, we process groups of size 3. We extract 123 and 456, adding them to the groups list, which becomes 123, 456. Now, only 789 remains, and since it is fewer than 4 digits, we append it as a single group. At this stage, the groups list is 123, 456, 789. Finally, we combine these groups using the join method, resulting in the formatted string 123-456-789. This final output adheres to all the formatting rules and demonstrates the algorithm's effectiveness in handling a typical input. The provided solution tackles the problem of reformatting a phone number string into the desired format. Here's a thorough explanation. 1. Remove non-digit characters *. The first step creates a list digits that filters out all non-digit characters, spaces, dashes, etc., from the input string. This ensures we are only working with the raw numerical data. 2. Initialize variables *. The result list is initialized to store the group segments of the formatted phone number. Variables I, current index, and n, total number of digits, are used to track progress through the digits list. 3. Process blocks of 3 digits *a while loop processes the digits list, grouping digits into blocks of size 3. This loop continues until fewer than 4 digits remain. Each group of 3 digits is joined into a string and added to result. The index I is incremented by 3 after each iteration. 4. Handle the final 2 to 4 digits * once fewer than 4 digits remain. The code handles the special cases. If exactly 4 digits remain, they are split into 2 groups of size 2 each, e.g., 1234-12-34. Otherwise, the remaining digits, 2 or 3, are grouped together as a single segment. 5. Join and return the result *. The result list, which now contains all the formatted segments, is joined with dashes, to produce the final formatted phone number string. This string is returned as the output. This implementation handles all edge cases, such as input strings with no digits, very short numbers, or numbers that require splitting into multiple groups of 2 or 3. The code is efficient and concise, operating in O(n) time complexity where n is the length of the input string. Here, we begin by importing the necessary utilities and defining the solution class along with the reformat number method. The first step is to clean up the input string by removing any non-digit characters. We use a string builder to efficiently collect only the digits from the input. This is done by iterating over each character in the string and checking if it is a digit using character.isDigit. If it is, we append it to our string builder. Once we have a clean list of digits, we initialize a list to store the resulting formatted blocks and set up variables to track the current index and the total length of the digits. Next, we process the digits in blocks of 3 as long as there are more than 4 digits remaining. For each block, we use the substring method to extract 3 digits at a time, add this block to the result list, and then increment our index by 3 to move to the next block. This ensures that we handle the first part of the formatting logic efficiently. Once we have fewer than 4 digits left, we need to handle the remaining cases. If exactly 4 digits remain, we split them into 2 groups of 2 digits each and add them to the result list. For any other case, such as 2 or 3 digits remaining, we simply add them as a single block to the result list. Finally, after processing all the digits, we join the blocks together using dashes to create the properly formatted phone number. The string.join method is ideal for this, as it allows us to concatenate the blocks with a specified delimiter. The method then returns the formatted phone number as a string, completing the implementation. To solve the problem, we start by processing the input string January 23, 45.6. The first step is to remove all non-digit characters, leaving us with only the digits. After iterating through the input, the resulting list of digits is 1, 2, 3, 4, 5, 6. Next, we initialize our variables. The variable result will hold the formatted blocks of the phone number, while I is set to 0 to track our current position in the list. The length of the digits list, n, is calculated as 6. Now, we process the digits in blocks of 3. Since there are more than 4 digits remaining, we take the first 3 digits, combine them into a string 123, and add it to the result list. The index I is then updated to 3, reflecting that we've processed the first 3 digits. At this point, our result list contains one block, 123, and the index I is 3. Now, there are exactly 3 digits remaining, which means we can append all of them as a single block. Combining the digits from index 3 to the end gives us 456, which we add to the result list. The final state of the result list is 123, 456. With all digits processed, the last step is to join the blocks using dashes. When we join 123 and 456 with a dash, the formatted phone number becomes 123 to 456. The final output for this example is 123 to 456. Now, let's consider a second example with the input string 123.4 to 567. We start by removing all non-digit characters, leaving us with the digits 1, 2, 3, 4, 5, 6, 7. As before, we initialize our variables, result is an empty list, I is set to 0, and the total count of digits n is 7. Since there are more than 4 digits remaining, we take the first 3 digits, combine them into 123, and add this block to the result list. The index I is updated to 3 to reflect the digits we've processed so far. With I now at 3, our result list contains one block, 123. There are still more than 4 digits remaining, so we take the next 3 digits, 456, and add this block to the result list. After updating I to 6, only one digit remains to be processed. Since there is just one digit left, it is added as a single block, 7. At this stage, the result list contains 3 blocks, 123, 456, 7. In the final state, the result list is 123, 456, 7. The last step is to join these blocks with dashes. When we join 123, 456, and 7 with dashes, the formatted phone number becomes 123-456-7. The output for this example is 123-456-7. Now, for the third example, we start with the input string 123.4 to 5678. Removing all non-digit characters gives us the digits 1, 2, 3, 4, 5, 6, 7, 8. With the digits extracted, we initialize our variables. The result list starts empty, I is set to 0, and the total number of digits n is 8. Since there are more than 4 digits remaining, we take the first 3 digits, 123, and add this block to the result list. The index I is then updated to 3 to reflect the processed digits. At this point, our result list contains one block, 123, and I is 3. With I now at 3, there are still more than 4 digits left to process. We take the next 3 digits, 456, and add this block to the result list. The index I is updated to 6. Now, only 2 digits remain. Since there are 2 digits left, we append them as a single block, 78 foot. At this stage, the result list contains 3 blocks, 123, 456, 78. In the final step, we join the blocks in the result list with dashes. Combining 123, 456, and 78 with dashes gives the formatted phone number 123-456-78. The output for this example is 123-456-78. To determine the time complexity of our solution, we can break it into distinct steps. First, we have the operation of removing non-digit characters from the input string. This involves traversing the string once and filtering out non-numeric characters, which takes n time, where n is the length of the input string. After that, we process the digits in blocks of 3. The list of digits, which we extracted earlier, has a length of m, representing the numeric characters in the string. The while loop iterates through these digits in chunks of 3, appending each chunk to the result list. Since every iteration processes 3 digits, the total iterations depend on m, making this step m. Finally, handling the remaining digits outside of the loop, whether it's 2, 3, or 4 digits, requires constant time because the number of digits being processed is fixed. This means the time complexity for handling these remaining digits is 1. Now, when it comes to joining the formatted parts with dashes, the operation dash.join, result, combines the strings stored in the result list. The result list contains at most m/3 elements, as each chunk represents 3 digits. However, the joining operation ultimately involves iterating through all the characters in the result list, which takes m time. Putting it all together, the dominant operations are filtering the digits, which is n, and processing them into chunks, which is m. Since m is always less than or equal to n, because some characters in the input may not be digits, the overall time complexity simplifies to n. Shifting our focus to space complexity, we start by considering the storage for the digits list. This list contains only the numeric characters from the input string, so its size is proportional to m, which is m. Additionally, the result list stores the formatted chunks of digits. Each chunk is a string, and the total space required to store these strings is also proportional to the number of digits, meaning it requires m space. Temporary strings created during processing, such as when creating chunks or joining them, are small and limited to a constant size of 3 to 4 characters at a time. This means the temporary processing contributes only an 1 space overhead. Therefore, the overall space complexity is m, dominated by the storage requirements of the digits and result lists. Comparing this to a naive approach, where the input string is repeatedly modified to remove non-digits or insert dashes, this optimized solution avoids costly string concatenations. The naive approach could result in an n squared time complexity due to repeated string operations, whereas the optimized solution reduces this to n by leveraging lists for intermediate processing. Looking at the best, average, and worst-case scenarios, the time complexity remains n across all cases. In the best case, where the input contains only digits, such as 1, 2, 3, 4, 5, 6, 7, 8, 9, there's no need to filter non-digits, and all characters are processed directly in chunks. In the average case, where the input contains a mix of digits and non-digits, such as 12 to 34, 56, 789, the digit filtering step dominates, but the complexity is still n. Even in the worst case, where the input is mostly non-digits, such as ABCDEFGHIJ, the time complexity does not change, as all characters must still be traversed for filtering. To solidify this, the proof of our big O notation shows that filtering non-digits takes n, chunk processing takes m, and combining these chunks with dashes takes m. Since m is always less than or equal to n, all operations are bounded by n. Therefore, the overall time complexity is n, and the space complexity remains m. When working on the reformat phone number problem, there are several common mistakes to watch out for. First, failing to handle edge cases, such as inputs that contain no valid digits. This might happen with completely empty strings or strings composed entirely of non-digit characters, leading to errors like accessing invalid indexes or returning incorrect results. Another common mistake is mishandling leading zeros. For example, if you preserve leading zeros in the processed output when they're not required, it could result in misrepresented numbers, like 00123 being interpreted incorrectly. Additionally, overusing regular expressions when simpler string operations would suffice is another pitfall. While regex is powerful, it can introduce unnecessary performance overhead, and overly complex patterns can make your code harder to read and maintain. Now, let's consider two more frequent mistakes. Ignoring unexpected non-digit characters beyond the anticipated spaces or dashes is a risky assumption. For example, if the input contains letters or special symbols, failing to handle these properly might lead to runtime errors or incorrect outputs. Another issue arises from inefficient string operations, such as concatenating strings in a loop. This approach has an n² time complexity because each concatenation creates a new string, which can become extremely slow for large inputs. Instead, building a list of parts and joining them at the end is a more efficient method to avoid redundant operations. To perform well in interviews involving this problem, there are some key insights to keep in mind. First, the ability to recognize patterns is crucial. Extracting and processing relevant data from strings is a fundamental skill that applies to various problems, so focus on doing this efficiently. Preparing for edge cases is equally important. Always consider scenarios like empty strings, strings with only non-digit characters, or formats that don't fit the expected structure. Simplicity and clarity are your best allies. Use built-in functions and straightforward logic to make your code clean and readable. It's also helpful to discuss trade-offs between different approaches. For instance, while regex might simplify your implementation, it could introduce higher runtime costs. Finally, be ready for follow-up questions that extend the problem, such as handling floating point numbers, negative signs, or different formatting rules. These variations assess your adaptability and problem-solving depth. This problem also shares similarities with several other problems on LeetCode, which can help strengthen your understanding of string manipulation. For example, in LeetCode 13, Roman to integer, you'll practice parsing and converting strings into integers. LeetCode 125, valid palindrome, involves filtering characters and checking specific conditions, which is very relevant to this problem. If you're working on string compression, LeetCode 443 challenges you to manipulate strings efficiently, focusing on optimizing space usage. Finally, LeetCode 227, Basic Calculator 2, deals with parsing strings and handling operations, teaching you how to process strings while managing more complex logic. Exploring these problems will deepen your knowledge of string handling techniques and problem-solving strategies. There are several alternative approaches to solving the reformat phone number problem, each with its trade-offs. A brute force approach involves manually iterating through the string and checking each character to determine if it's a digit. While this method is simple and easy to implement, it can become verbose and is less efficient for larger inputs. Using regular expressions is another option. Regex allows you to directly extract digits in a compact and expressive way. However, it may perform slower on very large strings and can be harder to understand for those unfamiliar with regex syntax. A more Pythonic approach involves using list comprehension or filter functions to collect digits and then joining them into the final string. This method is clean and efficient, but it requires some familiarity with functional programming concepts. Finally, for variations of this problem that involve removing specific characters while maintaining order, a two-pointer approach could be useful. This technique is efficient in certain scenarios but might be unnecessary for simpler tasks like the one at hand. Great work! To wrap up, we summarized the key elements of solving reformat phone number, highlighted important takeaways, and emphasized the importance of string manipulation skills. Thanks for joining me, and I look forward to seeing you in the next coding session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!